So I'm not sure I've told this one before, but one hydrogen atom says to another, "Oh no, I lost a excuse me. Oh no, I lost an electron." And the other hydrogen atom says, "Are you sure?" And the first one says, "Yes, I'm positive." Okay, so where we are is we are finishing up the chapter on magnetic fields and forces on current carrying wires and forces on current carriers. And the last thing that we need to do in this chapter is torque on a current carrying loop. And then we will move on to the next chapter, which is calculating magnetic fields from currents. Calculating magnetic fields from currents is a slightly longer chapter. That'll take us all of 3 or 4 classes at least. Okay. So I'm just going to do this rather quickly because we've already done this in lab. Hopefully by the time that you've seen this video, you've seen this in lab. So let's say I have a current carrying loop and a constant magnetic field. So let's say I don't want to have to draw too many x's, but my x's are a magnetic field which is pointing into the page. And my current carrying loop is the black square, which is carrying a current, and it will just say in the clockwise direction. And you might ask, how do we get current to go in a current carrying loop in a clockwise direction? Well, actually what we can do is we can have a coil, and a coil is made up of a bunch of loops, and this could just be a single loop of a coil. And so while it is spirally, each individual loop is like a each individual loop of the coil is sort of like a two-dimensional loop. And it could be circular, but let's just start with square. So, what is the net force on this loop? I believe that we've done this in lab, but let me review the net force on this loop. The net force on this loop is going to be the force on the top, plus the force on the right, plus the force on the bottom, plus the force on the left. So we've got to do each of those separately, right? So we're going to have the magnetic force on the, I said top, oh gosh. We finish writing this out. Let's just say that let's say it's a rectangular loop. It doesn't have to be a square loop. Doesn't really matter. And we'll say it's got a width of W and a height of H. And we can figure out each one of those widths or heights, each one of those current carrying wires, which are 4 together to make this rectangular loop, is a straight wire in a constant field, so we can treat each one separately. And so now let's go to the equations. The force on the top is the current I times the width W times the magnetic field B, which was a constant, times the sine of the angle between the current and the magnetic field. The current is to the right, the magnetic field is into the page. Use the right-hand rule, and therefore it's 90 degrees. Using the right-hand rule, current to the right, magnetic field into the page. Do it for yourself, but I'm going to do it now. It is in the upward direction. Okay. On the right, the magnitude is I, L, B, sine, and the angle between the current and the magnetic field is still 90 degrees. And the direction, point your fingers in the direction of the current, put them towards the magnetic field, and it is to the right. And then we know that the givens are not L, but the given variables are that length is H, so I'm going to turn the L into an H. Very convenient. IHB. Okay, so then the force on the bottom loop, you should be able to do this now, is the magnitude of the current times the magnitude of the length, W, times the magnitude of the field, B. Again, B, I, W, H are the givens, right? You got to get used to it. I could say B is 1 Tesla. I could say W is 1 meter. I could say H is 17 meters. I could say I is 30 amps, and you could plug in those numbers, but those are the given variables, and I'm going to leave it in terms of variables. The bottom, sine 90 degrees still, because the direction between the current and the field is 90 degrees. and the angle, sorry. And the direction here, your fingers go towards I to the left, they curl towards the magnetic field into the page, and so the direction is down. And then last is on the left, IHB sine 90 degrees, and IB is to the left. So make sure, yeah, okay. The direction on so this indicates the side on the left. This indicates the direction of the force. Okay. So what is the, first of all, what is the net force on this loop? What is the net force on this loop? The net force, the total force, FB net, is FB top, sum of the forces on the four pieces, the total force, the net force on this loop, right? So that's asked what's the net force on a loop, a rectangular loop in a constant magnetic field B with the orientation as shown. So if we add these up, notice that we get this one plus this one equals 0 because it's the same magnitude in the opposite direction. By the way, the sine 90s go away. They're just 1. So it's IWB up plus IWB down, and so that's 0 because those are vectors. And then this is IHB to the right and IHB to the left, so that's 0. So the net force is 0. There is no net force on this loop. But actually, even though there's no net force on the loop, does that mean there's no forces on the loop? There are forces. And what do actually the forces do? It's interesting to think about what the forces do, right? The forces, on the right, this is the force, and the force here, and the force here, making sure I get the direction of the force right, and the force there. What is the force trying to do? What the force is trying to do is trying to force the rectangular loop to be a circular loop. Right, if those forces, right, because there's forces everywhere there's forces everywhere along each side. So those forces are all pulling outwards, and by pulling outwards, what they're going to do is, if the loop was allowed to move, it would turn into a circle. Interesting, right? I think it's kind of cool. So the next thing we'll do, and I'll wait until the next class, is to turn the loop at a different angle to the field and see what the difference is. And let me do a little bit of foreshadowing and ask, what's the net torque on this loop? Remember what a torque is? It's a force that rotates a loop. Are these forces rotating the loop about any axis? No, they're not. So the net torque here is 0. We'll visit torque on a loop next time.